Recording. All right, students will be able to find Taylor and Maclaurin polynomials. Find the 7th degree Taylor polynomial centered at x equals pi if f of x equals sine of x. So the first step on these is to find f of pi. We find the point. So sine of pi is 0. So when I create this polynomial, I always need to have the point pi 0. We can't lose that. That's where we're centering the polynomial at. No matter how much I add to it, it will always have to give me 0 when I plug in pi. So then we do the first derivative, and we're going all the way to the 7th derivative, but there will be a pattern. This is cosine of pi, which is -1. Second derivative is negative sine of pi, which is 0. Third derivative is negative cosine of pi, which is 1 actually, because it's -1. But now when we hit the fourth derivative on sine and cosine, we should be back to where we started. And the derivative of negative cosine is sine. And now we're back to where we started. So the fifth derivative, I already know is -1 because this is all going to repeat. Sixth derivative is 0, and finally the 7th derivative is 1. Because they're all going to repeat. All right, now the polynomial. Well, the 7th degree polynomial of x is equal to the linear part. The x to the 0 part is 0. And then the x, so this is really for the x to the 0. This is for the first. This is the x squared, x to the third, and so on. This is for x to the fourth. That's for x to the fifth, sixth, and that's for x to the 7th. So all of the evens are 0. All the evens are 0. The odds go -1, 1, -1, 1. But when I plug pi in, I need 0. So if I just put negative x to the first, like right here, for -1, if I plug pi in that, I don't get pi, or I don't get 0, I get pi. So if we go minus pi, now when I plug in pi, we do get 0. And it's easy, it's that easy. That's the fix. So when you're centered at pi, you'll have x minus pi's. If we were centered at 3, they'd all be x minus 3's. It's that easy. It's pretty simple. All right. But then we have plus x minus pi to the third over 3 factorial. X to the fifth, so it'd be minus x minus pi to the fifth over 5 factorial. And finally, plus x minus pi to the 7th over 7 factorial. So there it is. Now it doesn't say to test it, but let's do it anyway. Let's find f of, how about pi is 3.14159, keep on going. So how about we find f of 3.2, something close to pi. Something simple, but something close to pi. How about 3.2? The 7th degree Taylor polynomial of 3.2, we'll find that also. And then let's find the error. No, not on this. We won't find error on this because sine and cosine are accurate to a whole bunch of decimal places. Let's grab calculators if you want to play along. This is the kind of stuff that we're trying to get to. I was doing notes for later on in the year. All right, sine of something close to pi. And we chose sine of 3.2. Negative 0.0583741434. That should be exactly the same. Sine and cosine are accurate very quickly. 3.2 minus pi plus 3.2 minus pi squared, but then divided by, oh no, I don't have the squared, I have the third. This is sine to the third divided by 6 minus 3.2 minus pi raised to the fifth. I did have the minus there, that's good. Divided by 120, and then finally plus 3.2 minus pi raised to the seventh, divided by, I don't have 7 factorial memorized. There we go, there we have it. Negative 0.05837414434. It's already accurate to 10 decimal places, and maybe more. So sine and cosine converge quickly, very quickly. You don't have to have a lot of terms to be very accurate. All right, what else we got? This is page 8, so let's go to page 8 in the packet. Taylor polynomials and approximations. Polynomial functions can be used to approximate other elementary functions, such as sine of x, e to the x, cosine of x, and natural log of x. On your calculator, graph these two. We've already done this. I'll just say this is, they're really close. The polynomial gets accurate pretty quickly, but it'll trail off. You know, sine does this. Oh, that wouldn't be the center. Where would the center be? Right here. And this polynomial is probably doing something like that. That's probably what it's doing. Right there. Definition of an nth degree Taylor polynomial. If f has n derivatives at x equals c, then the polynomial, here's your f of c, here's your f prime at c, here's your second derivative at c, third derivative, and so on, divided by 2 factorial, 3 factorial, 4 factorial. And then when it's centered at c, we have to have x minus c, like we did back here where we had x minus pi. So that when we plug pi in, we get the value we need. So there's just a really formal way to write it. That's called the nth degree Taylor polynomial for f at c, named after Brooke Taylor, an English mathematician. If c equals 0, then this is called the nth degree Maclaurin, after an English mathematician called Colin Maclaurin. So Maclaurins are always centered at 0. Taylors are usually not centered at 0, but they can be. Find the Maclaurin polynomial of degree n equals 4 for this one. So f of 0 is equal to e to the 4 times 0, which is 1. The first derivative is 4e to the 4x, so that's 4 when we plug 0 in. Second derivative is 16e to the 4x, which is 16 when we plug 0 in, and then now we have 2 more to go. Third derivative, 64e to the 4x, that's 64, and the fourth derivative, 256 e to the 4x, which is 256. So the fourth degree polynomial is 1 plus 4x plus 16x squared over 2 factorial plus 64x to the third over 3 factorial, and then plus 256x to the fourth over 4 factorial. But can we use how would we use summation notation for this? N equals, that's over 0 factorial, 1 factorial, 2, and 3. So I'm going to start at 0. And 0, 1, 2, 3, 4. I'm going to go all the way up to n equals 4. And it looks like this is 2 to the 0. This is 2 to the 1. No, what was that? Yeah, 2 to the 1, 2 squared. Oh, no, it's 4. Excuse me. 4. Jeez. 4 to the 0, 4 to the 1, 4 to the 2, 4 to the 3. So isn't that 4x to the n over n factorial? There we go. I knew I'd get it. But it doesn't ask to write that. Find the Maclaurin polynomial of degree n. Oh, let's do this. Let's back up. Let's back up. What should we pick? How about 0.1? Because we're at 0. Let's go f of 0.1, and let's go p sub 4 of 0.1. Let's see how those compare. And we're not going to do this every single time, but I want to show you that not every function converges as quickly as sine and cosine. So 4 times 0.1. We'll call this the actual value. 1.491824698. We go 1 plus 4 times 0.1 plus 16 times 0.1 squared divided by 2 plus 64 times 0.1 to the third divided by 6, and then plus 256 times 0.1 to the fourth divided by 24. So this should be close. So this is only accurate to 3 decimal places, not 10, like we see with sine and cosine. So this is 1.49173333. Now the error on this, on the approximation, and I want to emphasize that error is always positive. So even if I accidentally subtract the wrong way, minus this, I ignore the fact that that's negative. So it's 0.123491365. That's the error in the approximation. Thank you. So it's still a pretty good approximation, in my opinion. It's just not as good as sine and cosine are. Not as quick as they are. Find the Maclaurin polynomial of degree n equals 6 for cosine. Then use p sub 6x to approximate the value of cosine. Go. Give that one a try. So those are your derivatives, right? And notice that, this is really for x to the 0, 1, 2, 3, 4, 5, and that's for x to the 6th. And all of the odds now, all of those odds are 0. So it's only the evens because cosine is an even function. So if it's an even function, what represents it must have even powers. So p sub 6 is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And you see that the even function has even powers. It must. So now we're going to find p sub 6 of 0.1. And that's the answer that they want. We want to see that approximation. So 1 minus 0.1 squared divided by 2. I got that plus 0.1 to the 4th divided by 24, and then minus 0.1 to the 6th divided by 720. So on a test or a quiz, I want to see 0.99500411653. But you can check yourself. You can go, well, what's cosine of 0.1 just to see. Yeah, I'm pretty confident I got it right. Now, we probably won't ask you that on a quiz. We'll probably ask you more something that's not as accurate as quick. So it's going to be different. So your calculator will show you some different answer. But we could ask you this. And we'll need to see that. Any questions on any of this right here? All right. Find the Taylor polynomial of degree n equals 6 for natural log of x at c equals 1. Use p sub 6 of x to approximate the value of natural log of 1.1. All right, get this one going, and then I'll catch up to you. What do you do here? Oh, is this back in the notes again? Or it's in the packet? Okay. So we start these with the function value. We can't do this one at 0 because the natural log of 0 is undefined. It approaches negative infinity. So the first derivative, 1 over x, we'll call that 1, but let's remind ourselves that that's x to the negative 1. So second derivative is negative x to the negative 2. That's negative 1. Third derivative is 2x to the negative 3. That's 2. I'm going to 6. All right, so 3 more. Here we go. Negative 6x, negative 4, negative 6. 5 is 24x to the negative 5. That's 24. And the sixth derivative is negative 120 x to the negative 6. And hopefully you recognize those numbers. 1, 1, 2, 6, 24, 120 is factorials. That's nice to recognize. All All right, I didn't leave myself, we're centering at 1, so I need a lot of room for this. P sub 6 is equal to, the linear one is 0, that's x to the 0. X to the first is 1, so x minus 1 times 1 minus x minus 1 squared over 2 factorial. And then, let's see, I got the 1 and the negative 1. 2 is for 3. So plus 2x minus 1 to the third over 3 factorial. Minus 6x minus 1 to the fourth over 4 factorial. 24x minus 1 to the fourth over, no, to the fifth over 5 factorial. And finally, minus 120x minus 1 to the sixth over 6 factorial. Now, sometimes it benefits us to reduce. Sometimes it kind of ruins the pattern if we reduce. So sometimes we like to reduce, sometimes we don't like to reduce. And you just have to, do these. You have to see them. I'll talk about when I want to reduce, when I like to, when I don't want to. But here I want to, because this polynomial, I'm kind of writing it out of order. I'm going to write it up here reduced, is x minus 1 minus x minus 1 squared over 2. Then the 2 cancels out the 2 down here with the factorial and leaves 3. Minus x minus 1 to the fourth. I feel like I'm the only one writing this down. Well, not necessarily. Nope. Nope. Plus x minus 1 to the fifth over 5, and finally minus x minus 1 to the sixth over 6. So it does benefit us to reduce this one. It does make it simpler. It doesn't ruin a pattern. As a matter of fact, it kind of reveals a pattern. So now we need p sub 6 of 1.1. Well, now all of those are going to be 0.1. 1.1 minus 1, all of them are 0.1. So that makes it a little easier to enter it in. So 0.1 minus 0.1 squared divided by 2. And then it goes plus 0.1 to the third divided by 3 minus 0.1 to the fourth divided by 4 plus 0.1 to the fifth divided by 5, and finally minus 0.1 to the sixth divided by 6. So that's the value we want to see, 0.09531016667. But to see if we're probably right, we check it. And it's, look how many, 1, 2, 3, 4, 5, 6, 7. That's accurate to 7 decimal places. And then it starts to fall apart. But if it says, then use p sub 6 of x to approximate the value of natural log of 1.1, I don't want this one. That's not the answer we're looking for. We're looking for that one. We're looking for the approximation. Next one, suppose that g is a function which has continuous derivatives, and that they have the function value, first, second, and third derivatives. Write the Taylor polynomial of degree 3 for g centered at 2. So p sub 3 of x is 3 minus 4 times x minus 2 plus 7 times x minus 2 squared over 2 factorial minus 5 times x minus 2 to the third over 3 factorial. There we go. So then you just write it out. Now what they're asking you is, here's all the information. Do you know where to put it? Sure. We like those. Not much work to be done. This is, do you know where to put all the information? Any questions on that one? Use the Taylor approximation for x near 0 to find this. Now, I'm going to follow the instructions, but before I do that, I'll show you how, if all I saw was this, if I didn't see the instructions, if that's all I saw in the test, here's what I would do. I would go e to the 0 minus 1 over 2 times 0. 1 minus 1 over 0. It's 0 over 0. L'Hopital's, right? Indeterminate form. L'Hopital's would be limit as x approaches 0 of e to the x over 2. So when we plug 0 in, we get 1/2. So the answer is 1/2. However, I did not follow the instructions. If you did that on this test and those were the instructions, I would give you nothing for this. Nothing. You didn't follow the instructions. But I wanted to show you what I would do if I didn't have instructions. If it said evaluate. Okay, here's follow the instructions. Here's give you 100% on the test. Limit as x approaches 0. E to the x, they're saying, can be approximated with that function right there. So we go 1 plus x squared over 2 factorial, x to the third over 3 factorial, minus 1, because then we'd have the minus 1 there, all over 2x. Well, the 1's are going to cancel out there. And now, instead of dividing by 2x, let's multiply by 1 over 2x. Let's multiply by the reciprocal. So that gives us the limit as x approaches 0 of x and x cancel out here. So that leaves 1/2. 1x cancels here, and we're left with plus x over 2 times 2 factorial. Because there's still 1x left. And we're distributing the 1/2 down, or the 2 in the denominator. So plus x squared over 2 times 3 factorial. Now when I plug 0 in, this becomes 0, this becomes 0, and I get the same answer of 1/2. So that'll give you full credit there. That's following the instructions. Given that p of 2 of x equals a plus bx plus cx squared is the second degree Taylor polynomial for f about x equals 0, what can you say about the signs of a, b, and c if f has the graph pictured at the right? Let's pick a point. It says centered at 0. So let's find p of 2 of 0. That's a plus 0 plus 0. So that's a. So I know I have the point 0a. And the point 0a is up here. Here's the point 0a. And 0a is above the x-axis. So a must be greater than 0. So we got a figured out. Now we need b and c. P prime at 0, if I take the derivative of this, is b plus 2cx. And if we plug 0 in, we get b. Well, first derivative talks about slope. So the slope there is positive. So b must be positive. Now it says justify. 0a is above the x-axis. The slope at x equals 0 is positive. And finally, the second derivative is the derivative of this right here. The derivative of the first derivative is just 2c. 2c. And concave down. At x equals 0. So c must be less than 0 because the concavity is down. Notice that with these Taylor polynomials, that you notice how it's written backwards. Usually we go x squared plus 4x minus 7, usually. Taylor polynomials are always written backwards by how you construct them. Notice all our constructions of these go in reverse order, right? So it's just, the context gives you how you're going to write these. Oh, I love this problem. I love it. You guys find that? Is this one back in the notes now? We're kind of going back and forth. Find the fifth degree Maclaurin polynomial for this one. Use the polynomial to estimate f of 0.1. All right. F of Maclaurin, f of 0. And since we're doing derivatives, we should probably write it like this. But when I plug 0 in, 1 to anything is 1. So I know the value is 1. But I wrote it as a power so that we could just use the power rule when we do derivatives. All right, find the next couple derivatives. I'll bet you get it wrong. You're wrong. You're right. Oh, wait a minute. Let me look. Where's your first derivative?
I just didn't do that wrong.
Yeah. So you're definitely wrong. Where's your first derivative? You're right. Good job. It's tricky. All right, I'm going to let you guys off the hook. You got to remember the chain rule. So f prime of 0 is, yeah, it would be negative 1 minus x to the negative 2, but then times the derivative of the inside negative 1. Easy to miss that. And I'll bet a lot of you did. A lot of people have this today because I went around all period and went, wrong, 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 wrong. But that's easy to miss. All right, so the derivative is 1 minus x to the negative 2. As a matter of fact, all of the derivatives will be positive because you're always multiplying by a negative, then you're always multiplying by a negative. All right, this answer, when we plug 0 in, is 1. Let's continue on now. Let's pick up the pace a little bit. 2, 1 minus x to negative 3. So that's 2. 6. How many am I going to? 5th degree. I'm almost there. 24. Anybody recognizing these numbers? Yeah, you bet. Factorial again. That's pretty common. Not in everything, but in some things. They're all positive. Don't forget the chain rule when you're doing these derivatives. It's okay to miss it here. I just don't want you to miss it on a quiz or a test. So now P sub 5 is 1 plus 1x plus 2x squared over 2 factorial plus 6x to the third over 3 factorial, 24x to the fourth over 4 factorial, and finally 120x to the fifth over 5 factorial. So would it serve us well to reduce here or not? What do you think? Yes, because what's happening? They're all reducing, aren't they? All reduced to 1. Because those are the factorials. So this is 1 plus x squared plus x to the third plus x to the fourth plus x to the fifth. It's the power, we call it the power series. Why do we call it the power series? It's all powers, right? It's all powers of x. That's the power series. Let's finish out the problem, and I got a little bit more to say about this. What time do we get out of here? Today is TA 26. Oh, I got time. I got time. Well, let's do this. Let's go. Let's find f of 0.1. And we'll compare that to P sub 5 of 0.1. So 1 divided by 1 minus 0.1, or 1 divided by 0.9. It's all 1s. Well, look at this. If you go 1 plus 0.1, and now I'm using the polynomial that we made. We get 1.1. But then plus 0.1 squared. Plus 0.1 to the third. See how we're accumulating those 1s. Plus 0.1 to the fourth. And finally, plus 0.1 to the fifth. So 1.1, 2, 3, 4, 5. But this keeps on going forever. So if you want it to be more accurate, just add on another term. You can be accurate to as many decimal places as you want. Now I'm going to stay on this one for a little while. Because there's so much to talk about on this one. I will stop short of what we're going to learn about this one eventually, but I love talking about this one. This right here, right there, looks a lot like the sum, the infinite sum of a geometric series, which is a sub 1 over 1 minus r. That's a tiny little formula that you learned last year in honors pre-calc, and probably maybe saw it in algebra 2 also. That is the infinite sum of a geometric series, where a sub 1 is equal to 1 in our case, and r is equal to x in our case, right here. So we start with 1, and we keep multiplying by x. So p sub n of x is start with 1, and then just keep multiplying by x. That's exactly what we got down here. So when I see this right here, when I see that function, I don't go through all this. That's not necessary. I know that's geometric. So if I were to give you this one, 3 over 1 minus x squared, there would be absolutely no reason to do all these derivatives for this one. That wouldn't be necessary. Because a sub 1 is 3, r is x squared. So p sub n of x for this one, however many you want, that's why I'm writing n. How many do you want? Is equal to 3 plus 3x squared plus 3x to the fourth plus 3x to the sixth plus keep on going. Not necessary to do all those derivatives if it's all they're giving me is a geometric formula. It's not necessary. Then we get into interval of convergence and all kinds of stuff. So we'll go on and on with that one. That's later. This is a polynomial. We typically see it with the highest power first, all the way down to the lowest power, but when we build these polynomials, we tend to do that in the opposite direction, just how it's built. These are not polynomials. Calculators work by changing a function to a polynomial and then evaluating that polynomial. So we're going to find polynomials for all of these functions eventually. We've done several of them already. Knowing these factorials makes your life a little bit easier in here. I have them memorized through 6 factorial. I don't have it memorized after that. Seems like after that we throw calculators at you and let you go to town on it. We'll finish with this. You find that page? The Maclaurin polynomials for sine e to the x and cosine of x. So p sub n of x here, sine is an odd function. So I should have the odd powers, starting with the power of 1. So x minus x to the third over 3 factorial. X to the 5th over 5 factorial. X to the 7th over 7 factorial. Plus keep going. This is a little ahead of the game. But n equals, I don't know, what should we do, 1? The series is 1 to infinity of negative 1 to the n plus 1. Because see, it alternates. 1, negative 1, 1, negative, positive, negative, positive, negative. So if I plug 1 into here, that's negative 1 squared. That's positive. X to the 2n, but if I plug 1 in, I get 2. I want that first one to be 1, so minus 1 over 2n minus 1 factorial. So there it is all summed up. That's a little ahead of the game. I'm not asking you to do that in the homework. It won't ask you to anyway. E to the x, all of the derivatives are e to the x, and all of the derivatives will be 1 when you plug 0 in. So it's 1 plus x squared over 2 factorial, x to the third over 3 factorial, x to the fourth over 4 factorial. Keep on going. I'd start at 0 on this one, and it's x to the n over n factorial. We could have started with 0 on the other one too. It would have been fine. We would just have to adjust it to fit. Then cosine, p sub n of x is, this is an even. This is an even function. That's an odd function. So I need all the even powers. 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. N equals 0 to infinity of, you want to tackle that? What would the summation notation be? And like I said a couple times, this is a little ahead of the game. You're almost right. I left a little space. It alternates. So negative 1 to the, if I put n, would that be okay? Negative 1 to the 0 is positive. Yep, so that'd be fine there. Very good. Very good. Easy to forget that it alternates. I forget all the time. You're going to have to remind me several times throughout the chapter. Oh, wait, you forgot the negative 1. Edna St. Vincent Millay, an early 20th century American poet referring to the experience of simultaneously seeing and understanding the geometric underpinnings of nature, wrote, Euclid alone has looked on beauty bare. In case you've never experienced that sort of reverie when gazing upon something geometric, we intend to give you that opportunity now. So this poet looked at this, saw it, understood it, and went, wow, geometrically, that's one of the most beautiful things I've ever seen. It's very cool. I think it's very cool. How sine and cosine converge very quickly with polynomials. Anyway, it was enough to inspire a poet.